Okay, thank you, everyone. Welcome to the 2018 Winternship, your VVC Crest-funded grant research. My name is TJ Kennedy. John Hoskins, we were the advisors for this year's group. The Winternship was a 5-year grant. We're now in our 4th year, and we're hoping that's going to get renewed.
For 5th year?
No, for the next 5 years, right?
Yeah,
okay.
There's some things in the works.
Okay, we're hoping that we'll be able to continue for the next 6 years, because we still have 1 year left on this grant. So any of you sitting here could possibly be standing up here in the next year or two. I'd like to have each of our associates introduce themselves and maybe tell you a little bit about what their career goals are before we begin.
So my name is Yun Kwan Lee. I'm trying to get into med school, so I'm trying to expose myself to a bunch of research and these kinds of internships here. Right now I'm a biochem major. I'll be transferring after this spring semester.
I'm Will Turner. This is my 2nd year at VVC, and I'm hoping to go into a graduate program in chemical engineering. So chemistry research is really what I'm really interested in. So this type of program lets me get early exposure to that, and it's something I really appreciate.
I'm Brendan Morin, and I now go to med school, and these internships, they really interest me, and something I've been wanting to do for a long time.
I am Nabil Assal. My major is neuroscience. My plans are to go to medical school, and this is my first internship, and I hope to be the first and not the last.
Hello, I'm Charles Hastings. I'm going for my 4-year degree in chemical engineering and possibly continuing that on to a higher degree in chemistry and analysis. First internship, a lot of fun. Hope you guys join next year. Thank you.
Hi, I'm Jeffrey Foreman. I'm actually trying to become an RN. I have great knowledge, and hopefully I can further my education in chemistry as well. Hopefully, once I'm done with the RN stuff, I can possibly come back and start working on transferring to maybe to a 4-year and try and maybe be a chem professor one day.
So our research was, how do I state this? It was about a component in hops. So as you all know, well, maybe not all know, but as you might know, hops are flowers of a hop plant that are popular for flavoring beer. Hops are responsible for the bitter or the citric flavors in beers. Many components found in hops are under basic research for their chemopreventative and other medicinal properties, such as anti-inflammatories, hypoallergenics, and even antibacterial. So one of the components in hops is xanthohumol, and this is what the structure looks like. So xanthohumol is a prenylated chalconoid of particular interest as a potential anti-cancer agent. It is a chalconoid because it contains this structure here, including this structure here as its core. And it is very hydrophobic because of this prenyl group right here. So current production methods or current extraction methods are to extract xanthohumol is to submerge them in liquid CO2, but that process is often unreliable, sometimes dangerous and expensive. So this molecule is oh my goodness, I'm losing track. This molecule remains in hops during the beer manufacturing process. So the beer industry, they boil these hops and they get something called a wort, which is the liquid that, you know, the water that collects all the some of the components, the flavors from the hops, and it's it's a red liquid. It's called wort, and that's what they use in the beer industry. So what they do with the leftover hops, the flowers itself, they toss that out. Now our molecule of interest, the xanthohumol, is mainly in the hops that are thrown out, often used for like animal feed and whatnot. So this very, you know, interesting, possibly a potential cancer agent, anti-cancer agent molecule is being thrown out and not being put to proper use. And again, this was the compound of interest in our internship.
So just for those of you who are non-chemists or don't have that much exposure in chemistry, we're going to briefly talk about the instrumentation that we used. The big one is GCMS, which is gas chromatograph mass spectrometer. And the principle is that you have a very long, skinny tube of copper packed with some sort of liner made from silicone and other compounds. And you run an inert gas through that at high temperature along with a sample of whatever you're trying to quantify. And as it goes through the very long, ours is like 33 meters long, the components separate by weight and other properties, and once they're separated, they're fed into another instrument, the mass spectrometer, the MS part of the GCMS, that blows it apart with a beam of ions and then measures the size of the fragments that get spit out. And you can use that to really identify what the different components of a mixture are, although it's fairly complicated, and once you actually do it, you can't use what you put through it, so it's really a last step in identifying something and really checking what your progress is like on a process. And our other instrument is the hydrogen NMR for nuclear magnetic resonance. And we didn't really use that, but it's kind of just something that we have access to. And what it does is it uses a very high energy magnet to apply energy to the molecules, and it measures the way that they sort of bounce back and forth. And that can tell you the positioning and the relations of the protons or the hydrogen atoms in the molecule to very precisely identify what it is. The problem is that it requires an extremely purified sample, and the equipment must be very meticulously clean, because if there's even a tiny bit of like water vapor on the sample you put in, then your result is completely destroyed and meaningless.
So another instrument that we use is known as the UV-Vis, and ultraviolet visible spectroscopy. It uses the light in the ultraviolet visible spectral range to determine the concentrations of substances in the solution. So what you would do is you would fill what's known as a cuvette, a small test tube-like thing, with your sample. And you would stick it in the machine, and it would fire the ultraviolet light at it, and then it would interpret what is the absorbance of them and show it to you. And that can help you identify what the sample is that you have placed inside. And then we also have an IR, which is infrared spectroscopy, and that uses infrared radiation to identify the chemical function groups. And it requires somewhat purified samples for the analysis, and that also, once you put your sample in on your salt plates, once you put that in and it reads them, it gives you a graph, and each graph is pretty specific to what to the sample that you put in, and you just read the peaks within the graph to identify what functional groups are inside your sample.
So Will and I partnered up during this internship to try and extract xanthohumol, and this is what we tried.
Yeah, so this is just a general overview diagram, and I'm going to assume that pretty much no one here knows how to read a process diagram, so I'll just skip right into describing what each of these individual steps are.
So step 0 was spending the hops. So what this is we would get dried hops, and we would boil them in water. So I don't know if you can see very clearly, but the things floating on the top, those are the hop flower, leaves, and the liquid here is what we would consider the wort. So what we did was we boiled the hops in water for about an hour, and this is what the beer industry actually does. They get the hops, and that's how they make IPA beer and whatnot. So after we boil it, we decant the wort from the wet hops, and we, for experimental purposes, we concentrated the wort, and we have it in our room. I wanted to bring the huge red concentrated wort to show you guys, but I couldn't do that. Anyway, we collect after we decant the wort off, we collect the hops, so all this stuff, and then we dried it in an oven overnight at around 80 degrees Celsius. So the boiling process removes the very highly water-soluble components from the hops, and as we mentioned earlier, our target, xanthohumol, is in the hops.
So the next step is because the boiling step gets the highly water-soluble components out, now we want to get the water-insoluble components out. So we use what's known as a soxhlet extractor. And we didn't have access to like a real one because they're extremely expensive. I don't know if you can see, but they're like $1,000 for a 500 milliliter one. So we kind of just jerry-rigged one together with glass, or we had it lying around. And yeah, so we run acetone through it. The acetone boils in this flask. It gets pushed up through a pressure equalizing tube right here, collects in the condenser, drips back down onto the hops, which are stored in this pressure equalized addition funnel. And then it sort of just soaks the hops in the acetone for a while. Then you open up the stopcock and let the acetone drip through. So the idea is that the acetone being pushed down from the condenser comes through at about the same rate as what's dripping out. So the hop oils and so forth it's dripping out, and you have fresh acetone being constantly washed over the hops, which makes the dissolving process much more efficient. And once we're done with the extraction, we really don't care about the acetone, so we distill it off to get rid of it. This is the apparatus we used, and we're really just trying to boil off the acetone, collect it in a flask for reuse, because it's still very good, pure acetone, and you don't want to just throw away liters of it for no reason. And the addition funnel is there so that we don't have to constantly take it apart whenever we have to add more solvent to distill. Like we were dealing with a liter or so for our experiment. And the boiling flask is only about 400 milliliters capacity, so having to take it apart 3 separate times without a lot of work.
So, could you go back to the previous one? Yeah. So after we distill off all the acetone, we're left with this very highly concentrated oil. So, we're left with this highly concentrated oil. Next slide. And then, so to this oil, we added water, and since the oils kind of clumped together, and it was very viscous, it was very sticky. It was like tar. And we thought that we kind of came to the conclusion that xanthohumol will probably be in the resin instead of, in the resin because of its hydrophobic nature. So by adding the water to it, it cleans out more of the water-soluble components in the tar, while we get the even more non-water soluble things here. So in this picture here is our prototype resin. So after we added water to the oil and we kind of left it overnight, it all clumped to this stir bar over here. And you leave it to air dry overnight, and this hard resin is formed. We also tried a way to make the resin without adding water, because adding water produced a lot less resin than just boiling the solvent off, so distilling it like even more. And with that, we were able to produce a much more softer resin, not as sticky, but not as pure since it still retains all the more water-soluble components.
So just to give you context on our time frame, we got through those last 3 steps in like the first week and a half. And then we spent the next 2.5 weeks trying to figure out what the heck we're going to do with that hard resin, because it was more pure than just hops and a lot easier to work with, but it's still a fairly long way from getting our target molecule, anthocumol. So something we tried was just redissolving the resin in various solvents, and some parts of the resin would dissolve in some solvents and not in others. So we'd run those dissolved portions through our GCMS, and this is what a typical section of the printout would look like. So the red is when we dissolved it in ethanol, and you can see that it has a peak here that nothing else has, and here, and so forth. So that tells us that whatever this is, it's probably an impurity that's taken in by the ethanol, so ethanol would probably not be a good choice because it holds on to more impurities than, say, dichloromethane or cyclohexane or various other solvents. Something else we tried was throwing in a strong base, sodium hydroxide, to the dissolved resin. The hope was that that would deprotonate the hydroxide groups in the xanthocumol molecule, make it a lot more water soluble, so it would be much easier to extract with water than it was in its natural state. That didn't really work as we expected, and it probably damaged our GC column, so just keep that in mind if you ever find yourself in a situation like that. Make sure you aren't blowing out your GC column that you need to use for your research. Something else we tried last week was we noticed that the boiling point of xanthocumol is something like 400 degrees Celsius higher than other hop components. So we tried just sticking our hard resin under a Bunsen burner and burning stuff off, which actually worked surprisingly well. There were only like 3 distinct components left over after it was boiled. We don't know what those are, but it was an improvement, and we're hoping that one of them is xanthocumol, and perhaps next year we could investigate that more vigorously. So really a problem that we encountered was what's known as the isomerization of xanthocumol. And the idea is that under basic, or according to certain literature sources, heat conditions, xanthocumol rearranges into isoxanthocumol, which is not really a molecule we want because it doesn't have the same interest as the anti-cancer drug. So really we're trying to work around this because most of our processes would produce this product as opposed to the xanthocumol version. But we really weren't able to determine whether it was our processes or if it just came like that in the hops, something happened to them during shipment or processing that caused this rearrangement to happen. So this is what really clued us into the existence of the isoxanthocumol. This really well-defined peak right here at 4.5 minutes is isoxanthocumol as identified by our library. And the R match it gave, which is the relative match of our analysis versus what NIST determined it to be, was 98.3%. So that's a fairly good match.
So following the success of Will and Unicorn's procedure with acetone and in which they actually extracted isoxanthocumol, we thought we could try to recreate their results, but instead using something that's more friendly, I guess. It's more safe for human consumption. So we went with a different solvent and we used ethanol. So we prepared the same Soxhlet procedure, but this time we used 1 liter of ethanol, and we used about 35 grams of dry spent hops, and these were 7 days old by then, and we don't know if that could change the results or not, but I think it's probably important to know. So then we did the exact same thing. We took that solvent extract, we distilled it to concentrated, and then once we had it pretty concentrated, we added more ethanol to redissolve it and washed it with water to precipitate out the resin. So following that procedure, we washed this resin, redissolved and washed it 4 times. And every single time we would wash it and precipitate it out, we would get even less resin out. Most of it would actually stay within the water, which seemed to be a problem because at the end, this is the total amount of resin we came up with. And so what we decided to do instead was boil off the water while stirring to see if we could get any more resin to precipitate out. And so we did this over 2 days, and after the first day we got a bit more resin, and at the final day we got the maximum amount of resin we could because all the water had been boiled off. So we got a total of about 0.16 grams of resin from about 35 grams of hops. So then we moved on to aqueous two-phase because that has really been the focus of the internship over the years. And we were trying to figure out a way to possibly isolate the xanthocumol using aqueous two-phase. So we researched and we found that the density of xanthocumol is 1.24 grams per ml. And we found 2 polymers that had close enough densities to it, one of them being polymethacrylic acid sodium salt and polydadmax solution, which stands for polydioldimethhyl ammonium chloride solution. And so we chose these 2 for the aqueous two-phase system, and we put them in a separatory funnel and marked off where they created 2 distinct layers. It's hard to see in this photo, but when you're really looking at it, you can see a clear line here. So we mixed it vigorously to make sure that the two-phase system was maintained and that it didn't go away, because some polymers only have a temporary two-phase system. So we added a sample that we had created earlier in which we just boiled hops. So we added 1 ml to it and shaked it very vigorously again, and all of it seemed to go into the top layer, the polydadmax layer. And so we took this and we separated it in a separatory funnel. And then we encountered a problem. We can't run any polymer in the GC or else it would plug up the column or completely wreck the column. So we had to think of a way to separate it from the polymer. In previous years, we couldn't just add any solvent and separate it because it might kill the enzyme we were working with last year. But this year we were working with something that's not alive, so we could basically do whatever we wanted to get it out, as long as we still kept the molecule we were looking for. So we added ethanol to it, and once we stirred it, we found that the polymer just balled up and fell to the bottom of the test tube, and the ethanol took on a yellow color, which we concluded was it just extracting everything that was in the polymer while leaving the polymer behind. And so this was a way that we found. We tried this with multiple polymers, and it did the exact same thing to all of them. So we think we found a pretty good way of separating the sample from the polymer. So we took the ethanol, and then we ran it in the GC. And so once we ran it in the GC, we got this, and what we found was pre-lupulin, and this we've never found in any other sample, only in the polymer sample. And this is another component of hops. So all these other peaks here are just other components that we had found before in other samples.
So after we conducted an extraction with spent hops, we decided that we're gonna use fresh hops. So we used 30 grams ground fresh hops with 500 ml of methanol using a sock-slit apparatus. Then we took the extract and we stored it in the fridge overnight to remove the wax out of the extract. So after that, we filtered the solution to remove the wax, and then this is how I filtered it, and then the resin was and then the solution was evaporated in a vacuum and then extracted with under reflex, which is basically boiling the resin to get more components out of our solution. So we used 80 ml of petroleum ether for 3 times, and then the residue that we were left with it was extracted with 40 ml of cold ether for 3 times. So the next step was obtaining the hard resin, and the procedure I followed was to dry and evaporate in vacuum the extract that I got from petroleum ether and ether, cold ether. So this is the hard resin that I got. And after reading a journal that we referenced, I dissolved the hard resin in methanol and 4% of lead acetate until no more precipitate was formed. Then I took the lead acetate and then filtered it, evaporated and then I ran it in the GCMS. So this is a picture of the GCMS data, and we found that the GCMS detected humulene and columpiolone, which are found significantly in hops, but I didn't find xanthohumol and isoxanthohumol. So I decided to take a different route and use the UV-Vis. But UV-Vis requires using a very purified sample. So before running our sample in the UV-Vis, I used a technique called column chromatography, which is shown in the picture right here. So what you do, you run a silica gel column, which is right here in white, and we put our sample at the top, and we keep adding our solvent, which was a mix with we took the solvent from the other group. It was DCM, acetic acid, and methanol. So we ran our column, and we got 44 fractions of 0.5 ml, and then we ran it in the UV-Vis spectrometer.
So these 44 fractions are basically 44 different samples, and each of those had to be, they were half mil, and the UV-Vis only accepts at least samples of 2 mil. So we had to add more of our solvent to it before it could be read. So we filled all 44 fractions with more solvent and then ran them. And once we ran them, we got this graph, and every single line in this graph is one sample. And so at the beginning, we were getting almost nothing because there was next to nothing so coming out of the column so far. But then in the next few fractions, we started getting peaks, and a pattern emerged. And we could tell that these few peaks here were basically the same molecule. But each one is higher because it's gaining concentration. It's becoming more concentrated with each sample. And then after a few more, it jumped up to the very top, the concentration, and it maintained there for a good 20 samples. And then towards the end, it started to taper off back down from the last few samples. So what we did is we took some of these fractions and ran them through TLC to see, because we noticed that there were different peaks in each sample. and a few of them had missing peaks, and that the next one did have. So we took fraction 8 and 9 and we ran them through TLC, and here we can see that fraction 8 has something up here, while fraction 9 has something down here. And for them to be the same thing in TLC, they have to share the exact same spot on the exact same, they have to have the exact same RF factor, the retention factor. And these two have different ones, which told us that these were two different compounds, which meant that the chromatography was actually separating our samples. Then we looked at fractions 18 and 24 because we noticed a couple differences there as well. And we found that fraction 18 contained two different components and fraction 24 contained only one component. So that again told us that we were separating our sample as well. And finally, we looked at fractions 26 and 27, and we found that there was also more separation in those two samples. It's interesting because most of these have 3 peaks, but at some points you only have 2 peaks. And even up here, this brown line right here, it doesn't have the 3rd peak at all. And some of them are just missing. This blue one just completely comes down like that. And we don't know what any of these compounds are, but we know that there are separate compounds in here. So the job is to maybe next year try to figure out what those are.
Okay, now our portion of the experiment was actually on the side of isolating the individual compounds that came out of the beer hops. Will and Yoon did some great work making some resins. Now, what I was really focusing on was TLC, also known as thin layer chromatography. And what TLC is, it is a chamber. It is filled with a mobile phase, which is a solvent. And then you take a TLC plate, which is a piece of plastic that has a silica gel on it. Now, once you place that gel plate inside of the chamber, it's going to travel, the solvent line will travel up. Now you place a sample on that TLC plate, and as that travels up, you can actually see the individual compounds that are within a sample. And that's the advantage of a TLC. It's a very quick way to see if you have isolation. Okay. Now, as I did this TLC, I used several mobile phases on several different samples, and the biggest difference between the mobile phases focused on polarity, more polar and less polar. Now TLC was used both at the beginning and the end of fractions during the sequence of a column on our side of the experiment. So you would take your original sample, place it on a TLC plate, and you would get individual fractions. I apologize, individual components. Now, as you took a TLC plate of a fraction, ideally you should get that same component, and that would mean that it was isolated, if it was in fact there. Now, to pick my mobile phase, I went through a long process here. Now, just to kind of show you what TLC means here, this is a plate. Now, they are actually white, but they have a UV dye inside of them, so this is actually a TLC plate under a UV lamp. And this is a blank plate, just to show you that whenever you run a TLC plate in the solvent, you're going to get a solvent line. And you're going to see this line in the continuing plates right here at the top. Doesn't really mean anything, just a solvent line. Okay, now the second and the third plates, these show kind of the difference in the solvents, mostly based on polarity. This one was equal parts acetic acid and dichloromethane. This is where you would put the original sample. And as it was in the chamber, you can see that it was pushed all the way to the top. There's nothing, a little bit of bleed, but it went all the way up. Now the next thing I tried was maybe not the next thing, there was a lot of steps in between. But I tried to make sure there was 27 parts dichloromethane, 3 parts methanol, 1 part acetic acid. What it did to the sample was it raised the sample, and it's kind of hard to see. There are individual fractions, but it kind of bleeds together. It's separated, but not great separation. Now, a final solvent that I did design on our mobile phase, I just named it J44, but what it is it's 40 parts dichloromethane, 3 parts methanol, 1 part acetic acid. And it's really cool what it did. Here was our original sample. There's a fraction here. Sorry, I apologize. There's going to be a spot here, a spot here, a spot here, there, and there. And those are actually individual components of the sample. So there's great separation, and ideally those should be individual. Move on. Okay, now the TLC was used with column chromatography. You place a sample on your TLC, your original sample. You put it in the chamber, and that's going to break into individual components, and you're going to be able to see them if you use a good mobile phase. Then as you take the fractions, you actually place that sample, the individual fraction, on another TLC. You're going to run it in the same mobile phase, and if that matches, if that spot matches, what they call the RF, the retention factor, matches the original one, then you have the same component. And it's a pure sample. There's nothing else in there. Okay. Let's see. Again, the separation. If you see the separation, it's the same in both the original and in the fraction. Then you have something that's pure. It contains no other components. There was a lot of work with this, and the rest of it is going to go into column chromatography. I did some column chromatography, but Jeffrey here did most of it, so we're going to hand it off to him.
Okay, so my job in this experiment was to run column chromatography. Column chromatography is used to purify and separate the sample. And this here is our glass rod here. Usually we would like to fill it to a certain height, because the higher your column is, the better separation you'll get and purified sample or fraction you'll get to basically run in the UV. The problems that we had with running the column was using organic substance. Organic materials. The organic material that we used was dichloromethane. Dichloromethane mixed with the silica gel, it actually changed the column into a transparent look here, and it actually started cracking. Those cracks will, and bubbles forming, this will interrupt your purifying your samples. That's what it normally does. So after running these a few times, or more than a few times, we decided to start running it with water. With water, it gave us a better column. As you can see, it's still a little bit transparent, but it's giving you more of a white look here. And it also helps your solvent, your sample, or your sample that you get, it helps it run through the column better. And so with that being said, the column height that we like to use is basically half of the column. So this here is a 30 mil column, so we use half of that, or try to get half of that. With that, that would be our desirable height. And then with that, we started running the solvents through the column. And with running the columns, after packing the columns efficiently, then it was time to collect our fractions. Now, each fraction comes out a little bit different. We started with a full mill first. The problem with running a full mill sample is every time you run a full mill sample, it's running the sample through, but it's not separating anything. Everything's going in, but the concentration is there. Then we went off into trying a quarter mill. Quarter mill sample, the concentration really wasn't there, but it separated very nicely. It separated very well. And then after we tried a few times, then we decided to run a half mill. Half mill is right in the middle. We got good concentration, plus we got great separation. As you can see here, you can see it running. This is actually, it's a still picture, but as you can see, it started here. We put the sample here, and it runs through very cleanly. And as you can see, if you can, you'll see our fractions being collected here. And they were pretty good fractions. So after collecting those fractions, we took the fractions to the UV Viz station where we could actually figure out if we can hit our target. This here is our reference peaks. Our reference peaks, our dotted line here is basically the isoxanthohumol that my partners have found. So me and Will tried to actually target this. So the peak here on this wavelength is approximately 240 to this wavelength here, which is approximately 280. So this is our actual chart that we actually did. With all of those fractions, we combined a few of them due to concentration. This gray line here has basically it has two fractions put together. So it gave us a high concentration. So it's probably meaning it was very yellow when we collected the fraction. But when you look at the blue and yellow, it has a lower concentration, but it has more fractions that we combine it together. So the fractions that we did collect here, they probably weren't as concentrated. So this is why this gray portion here is higher. So, but we did find some success. As you can see now, this is the reference. This is at a 240 to a 280. And if you look here at this sample here on the gray, and you look at this sample on the yellow and this sample on the blue, it ranges from a 240 peak to a 280 peak, which is here. And we believe that we may have possibly hit our target, so we're really happy about it. Hopefully with more time or more experience with this thing, we could possibly get what we're looking for. And that's pretty much it.
Yeah, so just some obstacles that we encountered over the course of the research. Really the biggest one was actually the GC. Now, most other publications that look at hop components, they use a technique called LCMS, or liquid chromatography, mass spectrometry. And it's basically the same thing, except instead of using an inert gas to push your samples through, you're using a liquid. And the advantage of this is it means you don't have to vaporize your sample, which means that if you're dealing with something that possibly undergoes thermal rearrangement, you don't have to worry about that, and the target molecules being changed while you're measuring them. So the other point is that with LCMS, you don't really have to worry about your components condensing out and jamming up the column, which we had happened to us at one point, and we had to cut off about a meter of our column and replace it. And really another big point was that we purchased a purified, very expensive sample of very pure xanthahumol from a chemical company. And the plan was that we would use that to compare against our method so that we could have a better understanding of how good our stuff is working, because we can compare it directly to the gold standard, so to speak. The problem was that we got an email about the day before we started that it wouldn't be shipping until about March. So, yeah, that wasn't really something we could work around. And if we had, another 2 months, that'd be great. We could integrate that, but we don't, so we can't.
So because we didn't have the gold standard xanthahumol samples, we had to kind of go old school and try a bunch of different analytical methods. And to do that, we had to try to find some prior research about xanthahumol or hops components, which we had very difficulty finding, a lot of difficulty in finding the research about xanthahumol. And another big issue with xanthahumol is its low natural abundance. So in one of the research papers that we've read is they used a kilogram of dried spent hops. So a kilogram of dried spent hops, and they used their extraction methods and whatnot, and what they yielded of xanthahumol, I think, was 50 milligrams from a kilogram of hops. And I don't know if you guys seen the pictures, but like this, like about yay much is like 40 grams or so. So they used like of just hops, yay much. So they used a kilogram of hops and got 50 milligrams of dimethyl-humol. That's a 0.005% yield. So we have to go huge macro scale to try and get detectable amounts of dimethyl-humol, and that was a very big problem for us.
Yeah, and another problem that we had was that some of these procedures that we were looking up required very specific chemicals, and that kind of just stopped us from being able to perform those procedures because we didn't have those chemicals available to us. And also, just another issue was that I feel like we didn't have enough time. There's 4 weeks go by so quickly, and you just want new experiments to try because you think you're getting something, and once you get to the end of it, you feel like you just didn't have enough time and you could have done something else.
An obstacle we had was the poor size on our TLC plates versus our column chromatography. They were close, but they didn't match. One was 30 angstroms, the other was 60 angstroms. And although it showed a similar separation, it may not be exactly the same column run. So that was an issue, for sure.
So just some possible ideas for maybe next year or for other researchers in related fields to do is to take a better look at that thermal rearrangement or base catalyzed rearrangement we were talking about. Because if you have a better understanding of why that happens, then you can possibly intervene, add a step to the extraction process so it doesn't. Like, for instance, if you add enough acid, does that make it unable to occur? Or if you convert the hydroxide group that undergoes the rearrangement to an ether group, would that work? Or is it just something that happens no matter what? You can't really stop it unless you use very meticulous, specific methods. And the other point is doing more investigation into the aqueous two-phase method that Brandon mentioned, which has really been the focus of this program in previous years that we didn't really get the chance to go more in depth in because we had all of our other focus matters that we were focused on. And thank you to the National Science Foundation CREST for funding this program, and Cal State San Bernardino, and the YouTube channel Nerd Rage for his idea on using the Soxhlet apparatus with the pressure funnel instead of buying the $1,000 piece of glass. Yeah.
That's it. Me or they will take any questions you guys might have. I knew it.
Absolutely, absolutely. So when you guys were extracting your resin and doing that, and you said one sample was more pure than the other, like what made your determination as to which method derived a more pure resin?
Fewer peaks on the GC printout, where the soft resin of just boiling off the acetone completely, that had quite a few more peaks in the 4 to 5 minute range, whereas the hard resin we got from adding the water, that was very clean up until about 11 minutes.
And any thoughts as to how to get a more pure sample in order to maybe next time run an NMR on that?
From what we have, I really say that the first step would be getting probably taking advantage of the fact that xanthocumol does have hydroxide groups, whereas most of the other oils like humulene and so forth don't. If these are very polar groups, whereas even though this is very non-polar, if you can somehow interact with this while, again, avoiding this thermal rearrangement, and that's like I was mentioning, if you can protect this group, then that would be, I would think, a very applicable route to go. Because, like I said, this is really the only molecule that we're looking at that has these relatively polar groups, whereas everything else is very, very non-polar.
And that's literally garbage. The brewing process throws that out in the garbage. And they developed one procedure that they showed at the beginning, that process diagram, which was original. They came up with it. The interesting thing about it was base catalyzed, which generated actual solid particulate, which could be filtered out. And then when we ran VGC is when we isolated the isoxanthyl human. And so we got to thinking, is this a thermal rearrangement or is it a base catalyzed rearrangement? So the first thought, of course, was if something is base catalyzed one way, it should be acid catalyzed the other way, right? So we monitored all this stuff. Like, this isn't a tenth of what they actually did. Monitored the pH very closely before the base catalyzed, they redid it, and then gently took the solution backwards using weakly concentrated acid, because there's a lot of places for acid to interact on that molecule. So we wanted to add it really slow, hoping the last bond formed would be the first bond broken, right? That's what we were hoping. But it didn't work. We couldn't generate back the xanthyl humol. So that led us to think that it had to be thermal. But then the soxylate with both ethanol, methanol, and acetone, we might have been reaching a top temperature of 70 degrees, 68 or 70 degrees, and we still couldn't find the xanthyl humol. So I'm beginning to wonder if it's there at all, first of all. But secondly, that would clearly be a reason why they use the supercritical CO2 for the isolation. You can monitor the temperature, maybe even keep it below 0, and that would prevent the thermal rearrangement. That's not a question we've resolved yet. We don't know if the conversion of that to click that button, John, to that seems like a relatively simple process, doesn't it? And real easy. We don't know if that's thermal or if it's chemical related. We know it happens though.
And for just a couple more questions. That you guys did the 7-year. What you did with the was it methanol? Is it ethanol with the 7-day-old hops?
Yeah.
And then you did fresh one with methanol. Is there a reason why you didn't do fresh ones with the ethanol?
We had tried before to just do like a sauce, a reflux extraction. And that's when we did that one, which we incorporated into the aqueous two-phase system. We just found pre-lupulone and humulene and all the other stuff. There was no xantho humulene, but we did make a resin using that.
And I'm assuming we don't have a rotovap.
We have a rotovap.
We do have a rotovap. Okay. And was that used at all for the
We used it.
You did?
use it. So you did use the rotovap. Okay.
It didn't work.
It just didn't work. Gotcha. Okay.
Yeah. We one of the things that was nice here, and that the first soxylate didn't show, but this one clearly shows, is that glass tube on the side. And what happens is we're boiling the solvent here. It's vaporizing. This is closed. So the vapor is flowing up this tube into the top, up into the top with the condenser, which you can't see, which is condensing it back down. And when you open this, what these guys discovered was the perfect match to get the drip rate equal to the vaporization rate. So what you essentially have is this pure flushing of pure solvent through the spent hops over a period of how many hours? Hours and hours. And they did try that, but what it allowed us to do was to keep our solvent. The rotovap, it's gone.
It's gone,
Yeah, so we were running through some solvent. We were using liters and liters of it, and this allowed us to just reuse it. And then when they were done, we just took that pure solvent, dumped it back in the container, something we should never do, but we knew it was pure.
Yeah, we actually ran out of acetone, John. We go to Home Depot and get some cans of it.
I didn't know that.
Yeah.
And then lastly for Will and Charles, for the column, you said it was having trouble because it was an organic solvent?
Yeah, the problem with the organic solvent, that DCM, the problem that we were having with that is, like I said, they're both volatile.
What was the solvent?
The solvent was
Dichloromethane.
dichlor. Yeah, the dichloromethane that we used before, that's all we used. But the thing that set it all off is when, like, the point I was trying to make is when you put water in here, you make a nice fine packed column. But when you use straight DCM, that's where these bubbles and cracks start to happen, and that ruins everything.
We're trying to save a step, you know, rather than pack a column of water and then flush it down through with your running
Yeah,
solvent.
that makes sense.
You know, trying to save a step. but
Yeah.
Can't do it, apparently.
And what's the research database that we have?
For the GC?
No, just in general, when they're trying, as I said, there was limited data.
Oh,
That
Google.
were just Google?
There's nothing out there. And anything that's out there was done by, you know, Jimmy's Brewing Journal.
Is there any way to get
South
tied
Utah.
into,
I hope
because-
there's
is there any way to get tied into, for just the Winternship, to get tied into the Cal State, the CSUSB?
I have.
There's you do have that.
There's just
Oh,
nothing
okay.
out
Just
there.
nothing.
I found some, but it was very, like we said, it was very limited.
Okay.
And some of it, like they said, like the one we found, it took massive quantity of stuff. And that one process at the beginning, with that, this thing, they had on the board, it was like,
Takes about a week.
it was like 15
Wow.
different column
Yeah,
extractions.
yeah.
It was just a ridiculous amount. So a lot of people were claiming, yes, we got xanthohumol, and we're like, these are adding to mines, because we can't find it at all.
Interesting.
And when you really examine the research, if you really look at it, they say things like xanthohumol to include any other flavonoid, and you think, wait a minute here, you know, we got that the first day. So
Huh.
I think that,
Interesting.
you know, I kind of tripped on this. But I think that hops, there are some components in there that clearly suggest that it's more than just a beer thing. Now, I know that there's finally a reputable group that's doing some stuff in Boise. They're going to be, they finally put some real money toward it, and these guys are going to do it. But you're going to find with the nutrition, you know, there's nutritional, you know, there's medicinal, there's all kinds of health benefits. And of course, we thought it was a flavonoid instead of crenellated flavonoid. Flavonoids are yellow. So we even broke open the hops and scraped away the little yellow stuff inside of it and tried to, it turned out to be exactly what it's pollen. You know? I mean, but you never know. There's nothing out there. So it was a fun project. A great group of guys.
Yeah, well, really, I know you guys, I know I was there, I seen you guys were put in long hours, and for the amount of data that you guys collected in a matter of 4.5, 5 weeks, like, really, that's a lot of data that you guys collected in such a short amount of time. You guys should definitely be proud of yourselves, you know.